Okay, let us continue the last scientific session now with Sebastían Pérez, and he will talk about resolving the FU Ori system with ALMA co-planar twin disks.
Hello, Privyet. Hello, everyone. Thank you very much for having me here, and thank you for staying for the last leg of the conference. It's been extremely educative for me. I am kind of new to this field. This is the first time I give a talk on this topic, and this week I have learned a huge amount of information about all these amazing phenomena. So, and also, it's kind of lucky that I'm at the end, so I don't have to give the introductions of everything again. I'll just build on what has been said already. And this is kind of a follow-up talk from what Antonio was showing earlier about the FU Oris with ALMA. So I'm going to start with a little introduction on FU Ori. I didn't know where FU Ori was. I mean, I knew it was on Orion somewhere, but I just wanted to know exactly where it was. And this is the Orion constellation on its back. It's a beautiful image by an amateur astronomer. I love this guy, Rogelio Bernal. And you see in red, all of the red stuff is the H-alpha emission. And if we zoom in this region here at the top, we see Betelgeuse, the famous Lambda Orion 09 massive star, really hot, Bellatrix over there. And Lambda Orion is ionizing all the sun here. And if you look at this is the infrared from WISE, you see all these beautiful PDR photodissociation regions and dusty environments, and there is this arc here that is facing Lambda Orion, and that it's actually shielding, if we go back to the optical image, it's shielding FU Ori from the radiation of that massive 09, really feisty star. So that's exactly where FU Orionis is, the prototype star for the class in Bernard 35, and it became famous. You've seen this many times. This is my version of the light curve. The outburst in 1937 was extremely rapid. It's like a very, very interesting, fascinating phenomena that it goes up several magnitudes in just 1 year, and it's been active ever since. All of this part of the light curve was, as you can read in the seminal Herbig 1966 paper, was collected by Miss Hofflet in 1939. It's just wanted to point out that it was very weird to me that all of the astronomers Herbig refers to in the papers are doctors or professors, but Dr. Hofflet was referred as a miss, which was like kind of a weird thing. And if you look, she did an amazing work here by looking at historic record of the magnitudes in FU Orionis. If you take a closer look to any part of the light curve of FU Orionis, Antonio showed this already at the end of his talk, you see significant variability in the light curve, that it's probably connected, as Antonio was mentioning, to UX-Ori phenomena as well. There must be something there that it's a similar mechanism affecting the light curve of the object. In 2007, FU Orionis was discovered to be a binary. The two stars were resolved in an optical image with a 3.6 meter telescope at Calar Alto in Spain. They were using adaptive optics with laser back then. And they resolved, this is the PSF, this is a companion of the PSF, so this is an artifact. And these are the two stars separated by 0.5 arc seconds. At the distance of FU Orioni, this is about 250 AU, with a new distance from Gaia 2, which is, we kind of believe, seems to be okay, consistent with the Orionis cloud. We have FU Ori North and FU Ori South. It's a binary system. In 2015, Antonio published this early science cycle 0 image of FU Orionis, where you can definitely see that it's two stars. It's not resolved. The distance between the stars is not resolved, but you can definitely see it's two of them. And then this is a 0.8 millimeter, only using 24 antennas, 380 meter baselines. Baobab Liu later used a much longer configuration of ALMA and also a long configuration, baseline configuration of the VLA, of the Jansky VLA, and resolved the distance between the two components of FU Ori, here at 30 gigahertz, and this is band 3 at 100 and something gigahertz. The disks must be tiny because this is decent resolution, and they are still not resolved. These are two unresolved sources. Baobab managed to compile the photometry of the two disks separately, resolved photometry, and started trying to fit a multi-component model, adding dust layers and a free zone, and he found out that you needed several components in the disk within 30 AU to explain the SED. This is the spectral energy distribution of the primary, FU Ori North. I forgot to mention that we believe FU Ori North is the active member of that association. So an interesting thing is that in order to fit the spectral energy distribution, you need this layer at the midplane to be hotter than the surface layer in the dust components. So it requires a temperature inversion, similar to what Simon Casasus was mentioning yesterday for VAA3 Ori. So we also need a temperature inversion here. Although the model here, these are not resolved, these are still unresolved observations of the disk. So it's really hard to tell. It's a little bit degenerate. But for FU Ori South, you don't need the temperature inversion. You need a much simpler model to explain the spectral energy distribution. So this is all very nice and consistent with the scenario where the northern component is the active star and the southern component is not active, that we know of. Motivation for our new ALMA observations that I wanted to show today with you, I wanted to share. First of all, we wanted to resolve the disks. We wanted to see what's the size of this. How much resolution do we need to actually start resolving these objects? And we wanted to start with the prototype, FU Orionis, calculate the geometry so we can input the geometry of the disks into the working models of the object. And the second part, we wanted to prove the kinematics because it's a binary system. We've been hearing from Edward's talk yesterday, for instance, that encounters and interactions can trigger these outbursts. So we wanted to study the kinematics. I'm going to start showing you, this is the image that we obtained with ALMA band 6, 1.3 millimeters. We finally managed to resolve the disks. This is the resolution of the observation, and these are the visibilities for each of the two disks. They're clearly resolved according to the visibility plot. They are not massively resolved. I mean, they still look like blobs, so it's not a very exciting image. We definitely resolved them along the minor axis of the beam. So we have finally resolved the disk components, the dust emitting regions of FU Ori. We did some modeling, and we managed to fit a profile just to get a sense of the size of the disk. If we have a disk, what it's more or less its characteristic size. It's surprisingly, they are both very similar in size. Moreover, we try to fit the inclination and position angles of both disks, and they have also very similar geometries. So they seem to share similar geometries. This one is less massive than this one. I'm talking about the disks, about the dust around the stars. But they do seem to have similar geometries as if they were twin disks. With the new inclination, we could revise the model by Zhao Wanzhou that has been mentioned during this conference, and the accretion rate went down a little bit. So it used to be 10 to the minus 4, now it's lower with the new inclination and with the new distance, because Zhao Wan assumed 500 parsec distance back in his paper, so we now know it's more like 400 parsecs. So that was what we learned from the new observations of the continuum. The baselines of our observations are 8 kilometers. This is not the best that ALMA can do, but it was a step forward. The kinematics, we wanted to trace using the 12CO emission. It's messy because these are embedded objects, so you have a lot of cloud. You have a lot of filaments and things going on, the outflows that Antonio was mentioning before, but we managed to see something. First of all, I wanted to show you, again, this is the image published by Liu et al. And Takami et al. From the Subaru telescope, the 8-meter telescope in Hawaii. And this is polarized light. And what we're seeing here is a lot of structure that is probably connected to what the gas is doing in the system. The images by ALMA that I was just showing is just the warm dust, the cold dust around the stars. This is telling us there is much more going on in the gas, because this is probably dust that is coupled to the gas that is reflecting all this light and it's in polarized. This is a polarized light image. I wanted to share with you a new image that we have with the sphere instrument at the VLT. This is not published yet, but you can see that there are much more features around the vicinity of the primary companion. Let me zoom in a little bit. So we have this arc again that is now much well defined. We have these bands that are going up in some weird fashion, and a lot of shadowing in the image. Remember, this is polarized scatter light, so we're seeing just the surface of what's happening here. With ALMA, we have the 12CO kinematics that I'm gonna go through the channels now. The systemic velocity of the system is about 11 kilometers per second. That's why I'm starting at the channel at 2 kilometers per second, so I'm going from the blue to the red. And as you can see in the image, there is a lot of emission coming from both stars. So we have gas in both disks. And as you can see, 1 or 2 kilometers per second away from the systemic velocity, you start seeing emission kinematic signatures connected to these features in the scatter light image. So the arc, the big arc that we knew from the scatter light image starts showing up at 2 kilometers per second in the blue part of the gas disk. And this is the arc again, somehow connecting to the star. The red dot here and the blue dot here are showing the positions of the FU Ori components, and the crosses show the geometry that we inferred from the continuum emission. So this is the PA of the disk, and the ratio between the two is kind of the inclination angle of the disk. And that's the systemic velocity, very patchy because you have all the foreground absorption, the cloud that you are trying to look through, it's blocking a lot of the photons from the 12CO. And then you go back and the emission is on the red side on the north side of the disk. This is red emission. So we think we have picked up Keplerian rotation. This is a moment one centered on the primary component of FU Orionis, and we definitely see blue-red Keplerian rotation that is somewhat consistent with the PA and inclination angle that we derived from the continuum. So we think we're on the right track here to prove the kinematics of the system. As I was mentioning before, I wanted to highlight that we have a kinematic counterpart in the 12CO from this big arc like shape that we see in the scatter light image. Now, if you ask me, I still don't know exactly what's going on here, because I mean, your question before to Antonio was like, do we see inflow? Because we have a degeneracy we have rotation of the disk and we have an inclination. But if you change the disk by 180 degrees, and you make it rotate in the other direction, we have different orientations for the geometry of the disk, and we can either say that this is inflowing or outflowing. So right now, I don't know if that piece of gas that is connected to the arc is actually coming in or coming out of the system. We tried the scenario of an encounter. Of course, run a little simulation with Nicolás Cuello in Chile. And this is very simple. This is a toy simulation that doesn't have any real physics apart from the gravitational interaction. But we are able to replicate part of the arc that's coming out of the primary. And although we don't have any real physics in this disk, this is an isothermal simulation, so we cannot really explain or try to connect with the mechanisms for the outbursts. We do see an increase, a massive increase in the mass accretion rate at a certain particular radius in the disk. But there is another explanation that these are predictions for scattered light from the same simulation, that I was just showing. And as you can see, if we assume that the arc is an out-of-plane feature in the disk of the primary component, we can certainly find a configuration of an encounter that helps explaining the feature. But there is a new idea that has been out for a month by Kees Toulmont. He published a paper in August this year that making the case for cloudlet accretion. So you have all this, in the first place, we wanted to observe these objects because they are in a crowded region. We know there are lots of stars, lots of young stars, and there's a lot of interactions going on there. And we thought maybe with an interaction we can explain the FU Ori and the outbursts and all that. But there is also fragments of cloud in this area. They have been observed. There is a size and mass distribution for the cloudlets. They go from 100 AU in size to 1,000 AU in size. And if your star is moving through the cloud, it can perfectly, capture one of these cloudlets. It's just a matter of having the right impact parameters for the interaction, And these are the simulations that they did. And if you have a piece of cloud and your star gets too close to it, it can accrete it or interact with it and produce very similar features that what we see in FU Ori. So it's a really nice idea. Also, it helps you feed some mass onto your disk so you can continue having more episodic accretion events. So I thought it was a really nice idea that I wanted to share too. And this is my summary slide. I have shown the long baseline observations of FU Orionis with ALMA. We have follow-up data that is higher resolution and deeper, so we can actually understand, prove, and map the flows in the system to say whether this is an inflowing or outflowing feature, what we see in the scattered light image. And I think that's all. I can take questions now. Thank you.
Thank you. Questions?
Yeah, just a question about the position angle. Malbet et al. In 2005 published near-infrared spectrometry and said the position angle was 45 degrees. And that's also what we find from polarization. So do you have any idea what's going on?
So if these disks were flat, I will be extremely surprised. And I think that number 45 degrees is more representative of the inner regions of the disk, right? What we're calculating here, it's the inclination and position angle of material that is beyond 10 AU in the disk. So it's like more like the outer regions of the disk. And I will be completely comfortable with the idea of a mild warp in the systems.
What for flare? Is flaring
flare disk for...
I mean, the difference if you just have a flare that is the angle that keeps.
I don't know, that's a very good point as well. Maybe it's just flaring. And sorry, the kinematics of the gas also supports the inclination angle and the PA that we obtain from the continuum. So.
Maybe position angle doesn't mean anything when you have an edge-on system, pull-on system.
But it's not pull-on.
No, but it's Polish one, right?
30 degrees.
Well, that's
36 degrees is definitely not pull-on. I mean, you get a lot of kinematics on 36 degrees.
it's unlikely. 60 degrees is the most likely inclination.
That is not true. I mean, for the systems in the cloud, they are in all directions. It's a very, like, they are in all random directions, I think.
Yeah, random is 60 degrees, that's my point.
Oh, yeah, that's nice.
Okay, we have to move on. Yeah, we have to move on, unfortunately. We can then later discuss. Okay, thank you again.